Welcome back to ECE 441A, 541A. Lab number 1 is due Friday. Homework number 3 is due a week from today. And exam number 2, just as a reminder so that you get that on your calendar, is the 24th of October. Yes? Yeah. So for the lab, you just need to turn in 1 copy per team. And I've created, it's too challenging to create, or it takes more time to create it, group drop boxes. So whichever team member wants to submit it, I will find it if you drop it into your particular drop box. You don't have to submit 3 different lab write-ups for each of the team members on your lab team. Is that okay? So I just need 1 report for each team. And hopefully that's going okay. Some of you may need to nudge your system a little bit harder to get it to overshoot. Yes? Yes, it will get more involved as we go into the additional labs, but I believe this first lab just needs 1 sheet. It's the write-up sheet that summarizes everything. As far as you need to probably keep a copy of that so that you have your system. We'll start building on that system in lab number 2. You need to figure out what are your parameters, your damping coefficient, B, your spring constant, K, and your hardware gain, K sub HW. But once you have those, you should be able to, that's basically what's collected on that first sheet for lab number 1. Today what I want to do is develop another state space representation. Again, this is for insight into what is going on in your system, and some representations provide different perspectives than others, and it allows you to see what will be forthcoming in lab number 2 when we start doing full state feedback. Then we will go into a little bit more detail on how do we go from the state space representation back into the transfer function. We quickly derived that transfer function. We want to dig a little bit deeper into that because now we want to understand some of the pieces of that, and one of those pieces is actually the state transition matrix. And that is now this e to the matrix AT that you need to learn how to compute, know how it's computed, and understand what it really means. It allows you to understand how you transition from one location in your state space to another location in your state space, and it gives you or provides you insight into the dynamics of how that happens. Let's then get started with another way of taking a transfer function into a state space, and this one is different. We're calling this the phase variable approach. The last one was the input feed forward approach, and while you're writing that, I will start to return homework number 2, and in the back of that folder is homework number 1. If you turned in a hard copy and you haven't yet collected that, it should be in the back of that folder. And I don't know that it's alphabetized or not, so it may take you a little bit to find your paper. Let's now go through this process of finding another state space representation from a transfer function, g of s. Again, let's have that b sub 2 s squared plus b1s plus b sub 0 over, and now let's use a's, subscripted a's for the denominator coefficients. Again, to find the transfer function between the input u and the output y, that's now this ratio of y over u. And what kind of a transfer function does this represent? Did we give it a particular name last time? It's strictly proper, isn't it? Its numerator degree is strictly less than the denominator degree, and this is now in the form that makes it convenient to immediately go into a block diagram representation or a state space representation. This new approach, or this new technique for finding the state space, is based on, to sort of keep in mind, a factoring of y over u, or really we are going to introduce a new auxiliary or intermediate variable, meaning we are now going to write this transfer function as two ratios, y over w, and if we introduce a w downstairs, we need to introduce the w upstairs. In a sense, we haven't changed anything, but what we do want to do is now partition or associate pieces of our original ratio of polynomials with these two factored forms of our system. And the piece that will be associated with the first piece is actually the numerator. And so we now will associate with the numerator b sub 2 s squared plus b1s plus b sub 0. This piece is what we are saying we will associate with the y over w. And then the other piece that's left over is 1 over the denominator polynomial. That piece we will then associate that with w over u. We'll start with w over u and we'll build up the dynamics of our system from that. That now contains the denominator. The denominator is what gives us our dynamics. If you found the roots of your denominator polynomial, that will tell you where your poles live. And if we wanted a stable system, where would we want those roots to live? In the left half plane. We'll work with that denominator polynomial first and this ratio w over u, and then we will figure out how we extract information from that dynamics into our input u, or into our input y, from this second relationship y over w. The way that we've defined w over u is 1 over s cubed plus a sub 2 s squared plus a1s plus a sub 0. We are now very comfortable, I hope, with cross-multiplying, inverse Laplace transforming. This we can now rewrite. If we solve for the highest derivative of w, how many derivatives will we have for w? W of t. 3, right? So now we will have the third derivative of y. We are going to isolate that on the left and then push everything else onto the right, which means we have a minus a sub 2 times the second derivative of w. Is it clear where that's coming from? I've cross-multiplied, I've inverse Laplace transformed, and now I'm trying to solve for the highest power of the derivative of w, which was, because the capital W was scaled by s cubed, we have a third derivative. I'm now going to put all the other terms on the right-hand side. And I can't forget that I actually do have a u because of the cross-multiplication process that I did in the first step. And did I miss a sign? Every time I hear a little chatter, I get a little nervous and I go, there's probably a mistake. Which, unfortunately, you don't have that feedback in an exam, right? Yeah, you don't be listening to distracting people that are mumbling or talking to themselves during the exam. Focus on your own exam. And I don't do that, I guess, when I'm lecturing, and that might help the lecture in terms of correction. Now what we want to do is you should be able to build a block diagram from this, an all-integrator block diagram. Meaning, consider the left side as the output of a summing junction. And let's consider all of these pieces to be the input to that same summing junction. In other words, the output of our summing junction in our block diagram, let me see if I can sort of squeeze that in here. That we're labeling as the triple derivative of W. If we integrate that once, running out of space, so let me if we integrate that once, coming out of that we have just the second derivative. We integrate that, we have the first derivative. Didn't you wish calculus was this easy? And you integrate that again. That's why we had analog computers, so we could just do our calculus. But we had to learn how to build up these integrators in the electrical lab with R's and C's and op amps. You know how to build an integrator. You can do that, and you know how to build gains. Now we have W of t. All of those W's and their derivatives allow us to actually build up everything on the right except for the input. And the input is pretty easy. We can just say, well, that's going to be one of the inputs to our summing junction. That's simply U of t. And now we start collecting. Maybe I made my integrator blocks a little too big, but here's now minus a sub 2 times W double prime minus a sub 1 times W prime. Oh boy, I've already messed up. Not too bad, but in terms of what you're going to say to me in a minute, you're really going to be frustrated. Why did I say that? And now I'm really... Does everybody see where that comes from? We've now created a way of solving this differential equation with an all-integrator block diagram. We've now simply said, oh, the output of the summing junction is the third derivative of W, and because of the way the system was specified in terms of these denominator coefficients of the A1, A0, and A2, we now have constructed an all-integrator block diagram that will solve that third-order differential equation. But that's not our system, is it? That's just a piece of it. That was the right-hand side. What we have to do, and here's where you're going to be upset at me, I'm going to cut my paper and tape in a little bit more space. Sorry. Because I want something between what I just wrote and the top of that diagram. Okay? I'm sorry. So now you'll have to do some fancy... Maybe you can squeeze it in. It's not needing that much room. I apologize for that. But even if I would have left that space, you would have said, why is he leaving that space? I'm not going to do that. Sorry. Where am I going? I'm trying to build up the full transfer function, and I need this second piece, this b sub 2s squared plus b1s plus b sub 0. And I had defined that to be y over w. So if I remind myself of what I had, I now have this y of s over w of s equaling b sub 2s squared plus b1s plus b sub 0. And we can take that into the time domain. Well, hopefully it's clear that I want to turn this into just one polynomial relationship in terms of y's and w's. With that, I can now inverse Laplace transform, and y of t now becomes b sub 2 w double prime plus b sub 1 w prime plus b sub 0 w of t. I needed to create, if I go back to this block diagram, there's no output there, is there? Yet. But if I combine those w's and their derivatives and combine them with the appropriate coefficients b0, b1, and b sub 2, I can build up my output response, y of t, in my all-integrator block diagram. Meaning, I'm going to now scale w with b sub 0. Now these are going to be the inputs to the summing junction. And this is the output. Now I need to do a b1, but I can go down here and grab the first derivative of w, scale that by b1, add that in. I have one more piece, which is going to be b sub 2 scaling the second derivative of w. I can access w, the second derivative, scale it by b sub 2, feed that into the input of that rightmost summing junction, and the output of that summing junction is the output that I needed, y of t. This is now a way to create another block diagram representation from a transfer function description. And this is different from the previous one that we looked at last time. But if you applied Mason's gain to both of those, you would get the same transfer function back, even though the state space or the block diagrams may look different. We now want to build or create a state space representation from this block diagram. And that would be a gift, right? If I gave that problem to you, and that's part of your homework problems, is building up a state space representation once you're given a block diagram. What's the strategy that we use to create a state space representation from an all-integrated block diagram? If we want now a state space representation and somebody provides you with this gift of an all-integrated block diagram, how do you build a state space representation? One way. Well, to obtain a state space, I could say pretty quickly there might be 3 different state space representations from this one block diagram. But what's the strategy that we employ to obtain a state space representation from a block diagram? Yes. We have to assign our states, and there's a particular place we put those states, isn't it? We put those states right at the output of each of the integrators. And this is why I said we could have 3 different ones coming up pretty quickly. I'm going to choose the rightmost integrator's output to be x sub 1. Somebody else could choose that to be x sub 3. That's why the state space representation is not unique. You'll get similar answers. They won't be the same because my x1 is not your x1. But they're consistent. They're equivalent state space representations. Let's now apply that strategy. If we now say, let's let our states be the outputs of the integrators, and for my particular choice, let me call that x sub 1. I hope that's what I picked before. Let me now call this, maybe I should do it below so that it's not so scrunched up. Let's call that this location x sub 2, and this location x sub 3. That's the strategy, is assign state variables as to the outputs of our integrators. That's how we build up our state space representation. And now we simply need to write equations that describe x1 prime, x2 prime, x3 prime, the first derivatives of each of those states. If I wanted to find x1 prime, I pointed to that. If you're at home watching this online, you probably missed that hint. But what is x1 prime? What's the first derivative of x1 equal to, just looking at this diagram? It's equal to a lot of things from that diagram, isn't it? But the one that you want it to be equal to is it needs to be some linear combination of x1, x2, x3, and u. Our derivatives of the states need to be equivalent or set equal to a linear combination of the states and input. We now need to write x1 prime in terms of x1 plus some x2 plus some x3, and those sums, or that underline, is just a constant value, plus some u. We want to fill in those blanks. If we go back to our diagram and say, okay, how do I combine x1, x2, and x3 to create x1 prime? First, you have to locate x1 prime, and that's not too hard. You just go on the input side of the integrator that produced as its output x1. The input side of that integrator, well, there's several things going on there, but you're interested in the signal going into that integrator. And what do we call that signal in terms of x1, x2, x3, and u? There's only one there, isn't it? It's just x sub 2. That maybe makes it a little more challenging to think about, but all we have right here is the signal that we've called x sub 2 in our state space representation. And that itself is also x1 prime. They're the same. Meaning now we can go here and fill in. We don't have any x1. We don't have any x3. We don't have any u. We just have x sub 2. If we do the same thing for the other two state components and find their time rates of change, what is the time rate of change of x sub 2 as a state variable? X sub 2 prime. That's just x3 again, isn't it? Or it is similar to what we had. This is now just x sub 3 of t. The interesting piece comes when we look at the first derivative of x sub 3. That now gives us a little bit more structure in our equation. x3 prime is just the output of that first or leftmost summing junction. That's, if we go now counterclockwise, that's u minus a sub 0 x1 minus a sub 1 x2 minus a sub 2 x3. That's x3 prime. Does everybody see that and where that's coming from? What did I just say? Let me do it in the order. It's minus a sub 0 x1 minus a sub 1 x sub 2 minus a sub 2 x sub 3 plus u. And what's y of t? I want to write this not in terms of the w's. The w's were these intermediate variables that I used to build this diagram. Now I need to talk in terms of x1s, x2s, x3s, and u's. Because this was a strictly proper transfer function, y should not contain a non-zero d value, a direct feed-through term. Do you see u coming over into that summing junction? No. So there is no d term in our state space representation. All we have are combination of our states. We have b sub 0 times x1, b sub 1 times x2, and b sub 2 times x sub 3. Questions on that? What's our state or our system matrix A? What's in the top row of that A matrix? I'm now looking to fill out the state space representation. X prime of t is equal to a x of t plus b u of t. And we've already found C. We've already found D. What is A? Dimensionally, what is A? You key off your states. There's 3, and you know A is square. A is 3 by 3. What are the dimensions on our input matrix B? It has to have the same number of rows as I have states, which is 3, and I only had one input. This was a single input, single output. I have one column for B. And now I need to populate those matrices. What's in the top row of the A matrix? I've written it out here in terms of the blues, haven't I? 0, 1, 0, and what's the top entry in my input matrix? 0. I can now complete that, and I can say this is now, as far as the top row, 0, 1, 0, 0. What about the second row of the A matrix? It's just pulling off x sub 3, isn't it? When it multiplies the state vector, I have 0, 0, 1. What about in my input? There was no input, was there, in the second row, or driving directly the second state's dynamics? And now in the A, or in the third row, minus a sub 0, minus a1, minus a sub 2, 1. And again, just for summary, C was b sub 0, b1, b2, d was 0. And now can you see, if somebody gave you a transfer function, what did we start with? Our g of s was b sub 2 s squared plus b1s plus b sub 0 over s cubed plus a sub 2 s squared plus a1s plus a sub 0. Now do you see how you would structurally create a state space representation by inspection? You can immediately pull those coefficients from the denominator and put those into the system matrix. The eigenvalues of your A matrix are the same as the poles of your denominator in your transfer function. Your numerator coefficients now appear in your output matrix. Your input matrix is structurally fixed to be 0, 0, 1. And because it was strictly proper, we have a direct feed-through matrix D equaling 0. Questions on that? Somebody now changes up the A, B, C, and D, and it's not in this nice structure. Now what we want to do is be able to get or find a capital G. Find the transfer function from capital A, B, C, and D. We want, because what have we just done? We went from transfer function to state space, and we had a couple of different ways of doing that. We had the input feed forward last time, and we had the phase variable this time. Meaning we now have a G of S, or a transfer function. We have a block diagram representation, and we have the state space. And we want to feel comfortable going back and forth. How would I go from block diagram to G of S? Block diagram algebra, or Mason's game. How did we do this? How do we go from a state space to a block diagram? We just went the other way, didn't we? We went from New York to Dallas. Now I'm asking you to go from Dallas to New York. How do you do that? By inspection? Okay, that's a valid answer, but what are you inspecting and how are you doing it? If I give you a state space, can you immediately start drawing some things down on your paper? You can put down a number of integrators, can't you? How many would you put down? However many states you have, you now populate a page full of integrators with, let's say, your system is fourth order, you now need 4 integrators. Now, what do you know about those integrators? If you have a state space representation and you want to go to a block diagram, what's special about those integrators, or the outputs of those integrators? Those are the states. So you know the inputs of those integrators are the first derivatives of your state. Now you can put summing junctions in front of those integrators and connect by inspection your block diagram. Does everybody understand that? That would be a gift, actually, if I gave that to you on an exam. If I said, here is a state space representation, sketch the all-integrator block diagram. We went the more interesting way. We went from block diagram to state space via G of S. So we went this way. What we want to do now is talk about going from state space to G of S. We've already introduced this expression for the transfer function in terms of state or system matrices. We know it's that. We've derived that a little bit, but let's now look at that in a little bit more depth, and we'll do that by starting at the very basic level. What we want to do now is look at the time and frequency domain representations. So when I say frequency domain, you may think transfer function or S-domain block diagram. When I say time domain, you might think all integrator block diagram are state space or differential equations. We can actually relate those. The time and frequency domain representations can be related for linear time-invariant systems. And as I said, let's start walking before we start jogging or running. Let's consider, just to get our blood flowing and the brain working on this problem, let's consider a scalar time-invariant system. By that, my capital A matrix, I'm going to just let it be a lowercase a, for it's just a scalar. I now have a capital A matrix that's 1 by 1. I have a capital B matrix that's 1 by 1. I have an output matrix that's 1 by 1. I'm going to have a strictly proper system. And since it's time invariant, all of those constant, or all those variables, A, B, and C, are just going to be constant. Meaning, I now have a state space representation that's first order. My A matrix is 1 by 1. Now my X is just one variable. It's not this tall, thin column. It is a column, but it's just one high. Let's now Laplace transform that. We want to find the transfer function, and we should be able to do that for a scalar system. Let's now Laplace transform that. Again, we're just trying to see what we can understand from this simple case, and then we will expand that to the higher dimensional case. If we Laplace transform the differential equation, what happens when you Laplace transform a derivative? And now let's keep track of all the pieces. Multiplication by s, that's, let's say, the easy piece, isn't it? So now that one, now I will capitalize my x. And now I have to include the initial condition, don't I? And here the hard part is remembering how that enters, but it's minus x at 0 minus. That's now the Laplace transform of the left-hand side, which is the derivative of our state variable x. Again, capital X is a scalar, so we can be dividing and multiplying and doing all sorts of fun things with this scalar, not worrying about whether things commute. What happens when I Laplace transform the right-hand side? If I Laplace transform little x of t, what happens? It's just capital X of s. It's so easy, it's hard. All we're doing is defining what we mean by the Laplace transform of little x of t. And a was a constant. That can be factored out. What about if we Laplace transform b u of t? Same thing. B is a constant. U of t, we are going to call its Laplace transform capital U of s. Let's now combine pieces so that we now have s minus a times capital X of s. I've moved all the capital X of s's to the left. Let me move that initial condition on over to the right. And let me solve for the Laplace transform of my state variable, capital X of s. I can now say that I have 1 over s minus a times a constant, which is my initial condition, plus b over s minus a B was a constant times U of S. Now what we want to is, that should be clear. All I did was divide through by SI minus A on all sides. What I want to do now is look at what makes up my state as a function of time. I want to inverse Laplace transform this, and I hope you can see now that the time response of my state is going to depend on two pieces: an initial condition piece, or a piece that is associated with the initial condition, and a piece that is associated with how I drive that system, or the input. Let's look at the first piece. And now we just have to remind ourselves what this looks like. The first piece, I want to inverse Laplace transform 1 over S minus A, because the initial condition is just a constant. What is this? You inverse Laplace transform, and this is why you brought table 2.3 to the exam, or you copied it from the kiosk, and then you didn't need it on the exam. Maybe it was helpful to just be there sitting next to your exam, having that table. But somewhere there might be this transform pair. Is there? What does this look like in the time domain? Are you playing with me? What's the inverse Laplace transform of 1 over S minus A? E to the AT, isn't it? And if A happened to be negative, then you have this decaying exponential, and you have 1 over S plus A on the left-hand side. We are going to give this particular expression, e to the AT, a new designation. This is going to be called the state transition, and in general it's going to be a matrix. Here it is a matrix. It's just a 1-by-1 matrix. We will call e to the AT our state transition matrix. That tells us how the dynamics of our system behave, how they transition. If A was minus 2, then we know if we went up and kicked our system, it naturally would decay as e to the minus 2t. If A was minus 10 and we kicked our system, or we established an initial condition, we would decay at e to the minus 10t. That's how our system naturally responds, and that's how it will respond to an initial condition. The other piece is now associated with the input, and let's just think of this as two different terms. I now have a product of transforms in the frequency domain. What does that produce in the time domain? I now have h of s times g of s This is in the frequency domain. Now, if you needed to have your instructor feel good about what you learned in their class, hint, hint, you now have a product in the frequency domain. What does that correspond to in the time domain? Convolution. Whatever h of s inverse Laplace transforms into, it will be h of t. G of s will be g of t. What's h of t going to be based on what you just told me? Well, I'm getting ahead of myself. Let's just write the convolution integral. That's now this integral from 0 to t of h of, let's say, t minus tau, g of tau d tau. And this is in the time domain. But we have specific structure for our h and g. We now need 1 over s minus a b u of s. to be inverse Laplace transform. 1 over s minus a, you just told me, was e to the at. But now if that's our h, we need our exponent, a times the argument, which is now t minus tau. In the convolution integral, this now becomes the integral from 0 to t, e to the a, t minus tau. The b is just a constant, but because we'll be dealing with matrices in a little bit, I'm going to put it in the right location. Even though it's a scalar, it could go anywhere. B times the inverse Laplace transform of u of s, which is just u of tau, but this is now our convolution integral, and we need it to have the dummy variable of integration. This is now the convolution integral that allows us to keep track of how the input gets processed through our system. What is this e to the a? That's our state transition matrix. So the natural behavior of our system does influence how the input gets pushed into the dynamics of our system. If we put these pieces together, we had part 1 and part 2. If we now inverse Laplace transform that capital X of s expression, we obtain our time domain waveform. We now can say that x of t in the time domain, I didn't know it was that exciting, but x of t is now equal to e to the at x of 0 minus plus the convolution integral, which is due to the input term, e to the a t minus tau b u of tau d tau. Now we can see that we have our state is made up of 2 parts. One part due to the initial condition and one part due to the input. If we have no input exciting our system, the only part of our state will be due to the initial condition. If we have 0 initial conditions, the only place that we will get movement in our state is through the input. But the input will be modified by how the state transition matrix interprets that information, e to the a, whatever that is. Now, if we do this for the vector case or in the multivariable case, again, we want to deal with the time invariant. That means all of our matrices are constants. We now have an x prime equal to ax plus bu, and I think it was clear that that was a capital A and a capital B, just from the way I said it. No, from the way I wrote it, maybe. Y is equal to capital CX plus capital DU. And we aren't going to worry about having proper transfer functions. Let's just deal with the strictly proper case where A, B, and C are constant. Now I simply want to repeat the walking steps I was doing. Now I want to start jogging. What am I going to do? How did I approach the solution to our differential equation when it was in the scalar case? Really? My lecture was that meaningful? What did you do for that differential equation? X prime equal capital AX plus BU, or what did you do it when A was a scalar and B was a scalar? We just Laplace transformed, didn't we? Now we'll have to Laplace transform, but it's going to be a vector-based Laplace transform. Think about that while you're interviewing or visiting with companies, or maybe you can start talking about state transition matrices at the career fair and get a job. I'll see you on Friday.